We have an example problem here. A thin soap film with index of refraction n equals 1.35 hanging in air reflects red light with wavelength 682 nanometers. What is the minimum thickness of the film? So a thin soap film, this is essentially a bubble. That's not the best picture. So our film, the thin film itself, is what it says. The thin soap film, this has an index of refraction, it tells us, of 1.35. Hanging in air, we have air over here, we have air over here. With the way I've drawn it, the observer is on this right side. We're looking at it. When it says that it reflects red light, we're assuming that we're seeing the red light. This means constructive interference. So in terms of the table we have, we need to know whether n of the film and n of the surface, we need to know which one's bigger. So n of the surface and n of the film, in this case, the surface is always what the thin film is on, or whatever's on the other side of the thin film compared to the observer. So in this particular case, our surface is this air. So n of the surface is essentially 1 in this particular problem. N of the film, 1.35. So n of the film is greater than n of the surface. So on the table, we would look for the column that has n of the film greater than n of the surface. Now we have two equations. We have lambda sub c or lambda sub d, constructive or destructive. The constructive is what we want because we're seeing this red light. It tells us that it is reflecting this specific wavelength of light. So we want the constructive interference equation. So 2nd over m minus 1/2. Our allowed m values, 1, 2, 3, 4, 5, so forth. The question is asking us to find the minimum thickness of this film. D is thickness. So if I solve for D, because of these multiple m values, there's technically multiple thicknesses that will result in this constructive interference. But they want the minimum thickness. The smallest value of D as we vary m is going to be the smallest value of m. If we put in a larger value of m, we will get a larger value of D. So by plugging in 1 for m, that quantity, m minus 1/2, just becomes 1/2. And so D, we get that wavelength for constructive interference over 4n. So they tell us the wavelength is 682 nanometers. I'm going to leave it as nanometers. N in our equations, all of the equations, n is always for the film specifically. So the soap film has an index of refraction of 1.35. That's the value I will put in. I'm getting 126. And my units will be nanometers because that's what my wavelength was in. Index of refraction does not have units. Okay, so notice n of the surface is not used to actually calculate. I don't put that value in the equation anywhere. But n of the surface is important in determining which equations will give us constructive versus destructive. So we do need to know what it is, but as far as calculating for an answer, the only value of n that we put in is for the film itself. So this is a very thin film. And again, it's called thin film interference because these layers have to be quite thin in order to observe it.